So it is very important to know the why behind something, right? So when you get started with something, you need to know the why behind something. I have seen people asking me many times, why do we do data structures and algorithms? Because we have heard from our seniors that DSA is pretty boring and they have never used DSA in like 20 years of their corporate life. So why do we do DSA? Because it is tough. It is it takes just so much energy, and then all the teachers are proud of the fact that they can set really difficult questions on DSA. The interviewers are bragging about the fact that they can really torture you in interviews with questions from DSA, but no one uses DSA. But is that really true? I just want to know from you that do you think that DSA is just dry, boring knowledge, just like many of you thought about mathematics until you did physics? Then you saw that, okay, mathematics is useful for doing physics, but just plain mathematics sometimes look dry to many people. Right? So do you think DSA is the same thing? Any opinions on that? Okay, Soros thinks that it is quite interesting. Have you come across a situation where you had to kind of maybe you are pretty early to the game here, but I think many of you probably also know a little bit of DSA. Do you know the uses of this thing? Do you think we have already used some data structures in our C programming lectures?
Yes, sir. Like dynamic memory or multi-dimensional array.
Correct. So not so much the dynamic memory part, but arrays. Arrays are data structures, right? And Soros says recursion. Recursion is a paradigm of algorithms. Yes, so they're both included. Right? Strings are also data structures. Arrays are data structures. All right. So, and were they not useful? Were arrays not useful? They were. Arrays helped us organize similar kinds of things in a linear way so that accessing them is pretty fast, because you want to go somewhere, you can randomly go to any location, you can compute its memory address and go there and read or write data from it very fast. Right. So they were useful. So why behind the DSA? It's like you get the foundation of program. What do you mean by foundation? When you build a house, you make the foundation strong. The foundation is not strong, the house is probably prone to collapse from even a small earthquake, right? And you don't want to be in that situation, especially given the scenario these days when people are getting kicked out of jobs left and right. You need to have a very strong foundation. And that will not be true for all kinds of jobs, but many jobs these days would require a very strong foundation in programming at least. Because as you know, AI is taking over most of the jobs, and ChatGPT today can write most of the programs that humans found it difficult to write. So you need to be above and better than AI to be able to sustain a career. Sustain a career. I'm not even talking about flourishing, coming back with flying colors or whatnot in the career. At least sustain a career. You need to have a strong foundation of programming. So you use social media, right? So, and these are all those Mang or fan companies like Meta, which used to be Facebook, Twitter, which is now X. All of these companies, and they are the big companies which most of you want to go get a job there. So they use data structures a lot. I mean, many of the Indian companies, the IT companies may not use data structures very often, but these big ones, they definitely use a lot of data structures, especially graphs. And if you are a friend of somebody, they are a friend of somebody else, so you have a web of friends, right? So that basically is a graph for you. And when you look at maps, Google Maps, that is also something called as a quad graph. And if you buy things from Amazon, which I think most of us do, they deal with billions of items, right? And to store and retrieve them efficiently, you need data structures and efficient use of data structures. It has to be fast, right? You're searching through a billion items to look for your pen drive, and it takes like 2 days for Amazon to figure out how much it costs. Amazon would be out of business in 2 microseconds, right? You don't want that to happen. I mean, Amazon would that. So they will only hire people who have a strong foundation of programming, who know their stuff on data structures and algorithms, really, really well. That is one of the biggest reasons why you need to learn DSA. Um, and the second biggest reason, and some of them you might think about this as the first reason, is to enhance your problem solving skills. How do you improve your problem solving skills? I mean, how do you get muscles? You lift things, right? You have to lift heavy stuff to be able to get muscles in different parts of your body. How do you develop problem solving skills? Is you solve problems. You solve Sudoku. You become a Sudoku expert. You play chess. You become very good at that. You solve problems and you become good at solving problems, right? So as you will see throughout these 80 hours of the course that we'll be doing over the summer this time, is that we'll be solving a lot of problems, right? And one animation here is the Towers of Hanoi, which many of you wanted to solve during your C programming classes, but I just kept away from it because it might have intimidated a few students. But the rules are simple. There are like all these 3 towers and these blocks. You can only move one block at a time, and a bigger block cannot go on top of a smaller block. So it begins with the 3 blocks or the 4 blocks on one of the pegs here, and to move all of them to some other peg, right? Using the third one as the auxiliary peg. So you can solve this in like 5 or 6 lines of code, believe me. And you can use recursion. So the task for you today maybe is go think about this problem and solve this on paper without having to write code about this. And so you can solve, thousands of these problems. So whenever you are dealt a problem, so your manager tells you that we need to solve this thing by the end of today, come up with a nice way to do this so that the performance is better by 100%. It's like you double the performance. How do you do that? You don't have your tools ready in your neurons, right? Can you lift that heavy weight? You will not be able to lift that, right? If you have lifted like 50 kilos before, you might be able to lift 55 kilos. You have never lifted a book in your life, you will not be able to lift 55 kilos in one day. You cannot do that. So if you have solved thousands of these problems, you have your tools ready in your neurons, right? And so you will be able to synthesize a solution very, very fast, or at least know what to ask ChatGPT. You tell ChatGPT, solve this for me, it will not solve it for you. It will give all sorts of wrong answers. Your manager is going to figure out you use ChatGPT, and then because he's also using ChatGPT, and then it is going to be very bad for me. But if you can tell ChatGPT, I want to solve this problem, I think we should be able to use these strategies like recursion with a little bit of backtracking, with a little bit of the spattering of dynamic programming on that. I think we should be able to use hash tables. But so can you think of some idea with which you can connect all of these things and come up with something? And ChatGPT tells you, okay, we can do this. But then you tell ChatGPT, no, I don't think if we use that, that is going to speed things up way more than what you're telling me. And ChatGPT tells you, oh, I apologize for this thing. Okay, now we can do it this way, right? Or you can discuss the same thing with a friend instead of ChatGPT, and you can both come up with a solution by the end of the day. But how will you be able to do that unless you do not have the basic skills required for solving these kinds of things, right? So, and look at this maze solving. So let's just say you are, who is that guy, Abhimanyu, right? Who was lost in the Chakravyu. So you are that person and you are trying to go from this end to this end. So how will you solve the maze? This is a real world problem, right? What would you do? Anyone has any hints, or have you solved this problem before? Like if you are in a maze and let's just say you have a thread with you, a pool of thread. Thread matlab dhaga. So how do you go from one end and you have to come out of the other end? If you don't come out in time, you might die of thirst or hunger. So
reinforcement learning में भी ऐसा ही कुछ होता है, reward based system होता है. हम लोग जितने भी possible outcomes of movement है वो check करेंगे. If any possible movement restricts our movement further, we won't choose that path, we will choose the other path.
Sure, you can do that, but can we think of something simpler? Reinforcement learning, in reinforcement learning, there is a pattern. So like if I'm teaching my cat how to get to the room, and if you have to go through the maze multiple times, right? सुबह एक बार आ गए, रात को और एक बार फिर से आना है, अगले दिन फिर से सेम मेज में जाना है, तो रीइंफोर्समेंट लर्निंग काम करेगा. बार बार जाओगे तो कहाँ पे लेफ्ट लेना है, कहाँ पे राइट लेना है, तुमको रट जाएगा तुम्हारे माइंड में, है ना? दैट इज रीइंफोर्समेंट लर्निंग. अगर एक बार ही मेज को सॉल्व करना है जान बचाने के लिए, कैसे करोगे? इफ योर लाइफ इज एट स्टेक and if you want to go from one end of the maze to the other open end, how would you do that? If you have just a pool of thread with you and let's just say a piece of chalk and a pool of thread, what would you do? This problem can come in real life. It might. Let's just somebody kidnaps you someday, God forbid, and then you'll have to solve this problem. It had nothing to do with computer science, just pure common sense, right? But computer science will help you solve these kinds of problems, and you might have to solve extensions of these problems in real life later, right? So you start at this place and you have a pool of thread with you and a piece of chalk. So what do? Let's just say, you can see my mouse, right? So you start like this, and you take your pool of thread, right? And you put it on the ground. Here you have to turn right because there is no other way. And here you turn right again, and you are stuck here, right? And your pool of thread is lying on the ground, and you put an X here, saying that, okay, you have visited this place, and you come back. It's called as backtracking. So what do you do with the pool of thread? You start winding it on the pool again, and you come here, right? Then you have already taken this path, so you will not take that again. So what will you do? You will, let's just say you will take this path, down here, left, right, left, right? You keep doing that. Or maybe you just do this, and you're stuck here, right? So this is basically called as a depth first search, DFS. So you try to go as deep as possible until you cannot go any further. Then you try to backtrack to a place where there was a choice, right? So at the beginning, there was a choice. You could have gone left, you could have gone straight. So you do what? You do one thing. You randomly choose one of them. Right? You chose to go left. That led you nowhere. So then you came back, you backtracked to the point where there was a choice, you take the other choice. And when you take that choice, you go as deep as possible as you can, right? So you go this way, here, right? That's it, you're stuck. You put an X there, then you go back to the point where there was a choice. Like you come back here, there was a choice here. You could have gone this way or you could have gone this way, right? So you take the other choice. Then again you go, put the pool of thread, right? And you are stuck here. Where was the choice? The choice was here. Okay. Now you come back to that point, take the other choice. Let's just say you are stuck here. Again, you come back here, take the other choice. Go this way. If you do this, then eventually the deepest thing probably will take you out here. Right? Won't that work? Can you see that?
Yes, sir.
So this is basically your traditional depth first search. Think of this maze as a graph with edges connecting the nodes, right? And you can run your DFS algorithm to be able to come out of the maze. So this will improve your problem solving skills. We do similar kinds of problems hundreds of times. And when the opportunity comes for you to show your skills, to flex your muscles, you are able to do that. And you get a promotion and everyone is happy. Efficiency and scalability. What's the meaning of efficiency and scalability? What is efficiency? And people throw these words like left and right every time. Oh, efficiency, scalability, this, that. But has anyone paused to think about what is efficiency? What is efficient?
Ability to do a task in the shortest amount of time with a high level of accuracy.
Correct. Shortest amount of time, least amount of cost, least amount of space, the best of everything, right? स्पेस भी कम लेना है, पैसे भी कम लगने चाहिए, टाइम भी सबसे जल्दी होना चाहिए, तो वो एफिशिएंट कहला जाता है, ठीक है। और वो काम सही से होना चाहिए, ऐसा नहीं कि कम पैसे से, लाइक यू आर वेरी चीप with respect to time, money, and space, but what you do is completely inaccurate. It is inadequate. Then that efficiency is of no use. Okay. And what about scalability? Scalability, is our Google Meet today scalable? Yes, it is scalable, because today I'd probably be speaking to like thousands of students, and Google would be able to handle that for me, right? For me, sitting in this room with my cat, it would make no difference, right? I could be teaching one student, I could be teaching 5,000 students. It would make no difference. That is called scalability, right? Are the kid classrooms scalable? Beyond a point, they are not, right? I cannot pack 5,000 students in a classroom. I can't do that. The classroom will turn into a black hole, right? It's too much mass, right? So that is not possible. That is not scalable. So what is scalable? Almost similar effort, right? But you can scale it to millions or billions of people. Right? Software engineering is scalable. Write the software once, send it to make millions of copies and send it to many people. Hardware is not scalable that way. Like if I make a pen, I just cannot wish and say, okay, wish you could replicate into a billion pens and go to their homes. The pens are not going to work. But software can literally work on wires and go to their homes, with the blink of an eye. So how to design software that is efficient and scalable? Well, you need to know your data structures and the algorithms that work on those data structures really, really well. Right? That is why companies test you on these things. It's not just to trouble you, and it's not just for elimination. That कौन कितना रट के आया है लेट कोड में, कौन कितना समझा है, कौन कितना सॉल्व कर सकता है. White board पे खड़े हो, you need to stand in front of the whiteboard and ask questions to interviewers. Like, what do you want? Do you think the input should be sorted? Do you think the input is only numbers, or do you think there are infinite number of items coming in? You can ask many questions to them. They will help you. They appreciate that fact that you are able to communicate with them about the requirements for the problem. And you solve it piece by piece, right? They will help you out. But you should be able to come up with a solution. And then you will be hired, right? That is why Google search, it uses petabytes of information, right? The internet is really, really big. It goes through all those pages because of the links between the pages and runs an algorithm called as PageRank, right? If we ever do MapReduce later as part of big data, then you will know what PageRank is. It's a very small algorithm. It's like 5-6 lines of code, the basic version of that. But that is what Google does. So it uses data structures and algorithms to be able to do one of the biggest inventions, I would say, of the 21st century, which is Google search. We all do Google search, right? Google it. Now, there is a verb called just Google it. Was Google it there 20 years ago? Somebody said Google it, they'd be like, what is a Google? What do you mean by Google it? Google is not even a verb. But today, Google it is a very common usage. Streaming services like Netflix. We all know Netflix and many YouTube and whatnot. They stream data to billions of people, and the data itself is gigabytes in size. How do you think Netflix is able to manage that? So many different things. They distribute data geographically. How many servers do they hire per region? It depends on the load. They measure the load, times at which the load is very, very high, like night time maybe. People watch a lot of Netflix. What do they watch? What to keep? What not to keep? What quality to stream at? So many different things. And when they do all of that, it's a successful company like Netflix. So don't expect to know only Java and C and go work for Google or Netflix. It's not going to work out. Right? So I'm really surprised sometimes, and not in a bad way though, that when people say that nobody uses data structures and algorithms at their work, maybe you're working at the wrong place. Right? If you're working at the correct place, then you will not ask that question. Okay. And career opportunities. I'll not go through this anymore because I've been speaking about this for the best part of like whatever minutes we have covered until now. So you will be learning advanced topics later. Right? I mean, data structures is a basic topic. That's why they're teaching it to you in the first semester of second year, right? Otherwise, if this was so advanced, it'd be teaching it in PhD or MTech. Why are they teaching it in the third semester? Why are they doing that? Because there are other topics which will build up on your knowledge of data structures and algorithms. And what are those advanced topics? Well, AI, right? AI, the big demon called AI. When AI is not a living being, you need to understand how AI works, the science behind that, and create more AI. That's the only way you will remain relevant and you'll be able to keep a job, right? If you do not understand AI, if you cannot create your own AI, and why will you have a job? So to understand AI, you need to understand DSA for sure. This is a neural network, right? How many of you have heard of neural networks? I mean, there is one inside your brain right now, right? Your brain is made of neurons connected to each other using synapses, right? That transmit electrical signals. And the stronger the synapse, the more likely it is to fire, right? And that is how we learn. When we learn it once, those synapses are not strong. When you learn something again and again and again, like reinforce it, then what happens? Those synapses are strong. And you probably won't forget that very, very soon. Right? So here is a computer neural network that is being trained. So you're giving some handwriting, there's a 5 and we're training it. There's a 0, we're training it, telling it, okay, if you see something like this in handwriting, then make it a 5. If you see something like this, make it a 0. And you see the neurons, the input layer, the output layer, right? And they're connected by the synapses, right? The edges. And what does training do? It gives weights. कि कौन सा edge कितना भारी है, कौन सा synapse कितना तगड़ा है, right? So we train that, and then we have a model, a machine learning model. Right? So this entire thing, to be able to do these kinds of things, to be able to understand these things better, database systems. I think many of you will learn database in the second year. It uses B plus trees, right? That is something that we will probably not cover as part of our DSA here, but they will teach you in databases, right? Because that is advanced knowledge. Right? So unless you know basic trees, you'll not be able to understand B plus trees. Right? Unless you understand basic graphs, you will probably not be able to understand neural networks. So to be able to understand these things easily, you'll have to study and make some sacrifices in terms of your sleep and then mental peace. I'm just joking. Learning this and competitive programming. I think many of you already know about ICPC and Code Forces and many other things. Even KIT also organizes its own coding competitions. And there you are given a very strange problem. When you look at the problem, you're not really sure how to solve it. For the first 5 minutes, you're totally blank. Then what takes away that darkness? What takes away that blankness? Your knowledge of DSA. If you have no knowledge of DSA, the blankness will remain and you will just quit and go. But if you know DSA, then for 5 minutes you will all panic. Then after that, you will not panic. Right? The fear will go away and you'll be able to actually solve it. How? By employing what we will learn in the next 80 hours. Right? Okay. Any questions so far? So let's move on to kind of a brief overview of the topics that we will study, right? And I'll give you some illustrations and then I'll let you go, right? Just to make sure that you do not think of this subject as this huge behemoth of garbage. Just like many of us thought about mathematics back during our +2 days. Why are we doing this trigonometry? Why are we trying to solve sine square plus cos square plus this, a by 2, b by 3 is equal to this? That makes no sense, right? Properties of triangles. And oh my God, those huge identities that you have to solve. I used to find that pretty boring and dry. But when I got to apply many of that stuff in physics, then I started gaining a better taste of mathematics. Right? So just wanted to let you know that I'll go through a bunch of illustrations today, and all of them are there on the blog. You don't have to take notes or anything. I'll put up this recording for your reference later. But you'll have a good positive feeling probably when you leave this class, so that you come back hungrier next time. Okay. So we'll hit it off with an introduction to algorithms and complexity. What is complexity? When you write an algorithm, it has a certain amount of complexity in it. If it's written in a simple and efficient way, we're talking about efficiency, then it will take less time to run. It will take up less space while running. So we have time complexity and space complexity. If the algorithm is not very efficient, I mean, people can write it in a better way, but you have not done it in a better way, then maybe for small data sets, it might be the difference of time might be not noticeable. Maybe your thing might be running faster than their version. But if the data set is increased, like you're sorting 5 numbers, then sure, you can do it with pen and paper, and it will be faster than somebody writing a program, because they have to start the computer, write the program, compile it, fix the errors, and then run it on 5 numbers. I mean, they will take longer. You can do it faster just by, just hearing the numbers and doing it in your head and giving the answer. You can do that faster that way. But if I tell you to sort 5 million numbers, can you do that on pen and paper? It will take 50 years for you to do that, right? But a computer program can do it in like a few milliseconds. Right? So if you have more numbers and you want to do more numbers or more input, to the tune of like millions and billions and trillions, efficiency comes into the picture, right? Or the differences can be really, really huge. Something that takes 1 hour for 100 numbers might take, more than the lifetime of the universe to be able to compute it on 1 billion entries. It can blow up that way, that fast. So you need to write really, really efficient algorithms which can finish in time. So we'll be analyzing algorithms, and I'll be telling you tools and techniques how you can analyze the algorithms and specify that this is of this category. This varies linearly with n, this varies quadratically with n, like n square, n cube, polynomial, exponential, factorial, logarithmic, and all of these different classes of complexities are there. I'll be telling you the differences between those, right? And there are a few notations in that regard, big O, omega, and theta, and we'll see what that means, right? So this will probably take about 6 hours of our time, but this is very, very, very important, right? In your interviews, they will ask you this. So you write something, they tell you to, and they'll ask you, okay, now tell us the running time, the time complexity of this algorithm. You need to know how to analyze that and tell them accurately how much time it will take. If you're not able to do that, all the effort that you put writing the algorithm on the whiteboard is going to be wasted, because they will conclude that you had just remembered this from LeetCode and you have not actually understood it. Don't do that mistake. You will not get any job that way, right? Don't memorize anything from LeetCode. Understand, practice, and then go. Right? If you remember and you do not, if you have memorized the code, right? I have water. And you just wrote that on the whiteboard very, very fast, right? The efficiency of writing on the whiteboard is way higher than you able to explain the efficiency of the code, then you'll not get the job, right? Go slow. You know the solution, then pretend that you're trying to think about it. Or they'll conclude that, you just knew this before, and they'll give you a way tougher problem. You'll not be able to solve that. They'll kick you out. Then we will do basic data structures, like mostly linear data structures, like arrays. We have done arrays already. So we will go over arrays again, solve a few problems, like 10, 20 different problems. Arrays are the most common topics for your interviews. So we need to get our fingers warmed up using arrays and strings, right? So we'll do that. Then we'll move on to stacks and queues. So what's a stack? I mean, a stack is one thing kept on top of another thing going on top of that, right? So it's a stack. Like, your parents probably keep newspapers if they get any, if at all, right? One newspaper goes on top of another, and then you want to read something, then you have to go read the latest one. That's all, because the rest are all just packed somewhere at the bottom of the stack. So this is called as the last in, first out. Whatever goes last comes out first. Queues, we all know what queues are. And if you're standing in a queue, then if you come in late, then you will be serviced later. So we will see how to implement all of that. Then linked lists. What's the meaning of a linked list? What is linking? So the nodes are linked to each other, And so why do we use linked lists over arrays? It's a very, very common question in interviews. So if arrays are there and you can store your items in arrays, then why do you use lists, linked lists? And linked list questions are also very, very common. There was a time 15 years ago, the only questions they were asked were from linked lists. How do you find a loop in a linked list? How can you delete elements in a linked list? Those questions became so common that now they don't ask questions from this, because now it's assumed that almost every Tom, Dick and Harry knows about linked list. So you also know about it. We'll spend about 14 hours doing this. Then we will do recursion and backtracking. So what is recursion? Did we do recursion? I'm not sure all the people in my class are here. Or let me put it a different way. Everyone here is from my class. So I think some new people are here. So have all of you done recursion before? Has anyone not done recursion? What is recursion? Can someone tell me?
Sir, the method invoking itself.
Calling the function in itself.
Okay, that's correct. Both of them are correct, right? So recursion is a function calling itself with what? With a different set of what it got. So let's just say your main function calls a function and gives it something. So it checks, okay, if it is the final thing, just give it, right? No need to call yourself again. And it has to have a base case. It has to stop somewhere, right? And stopping, where to stop, you check at the beginning. But if you're not supposed to stop after the check, what do? You take a part of the problem, right? And then call yourself again. What happens? There is a method calling stack. So the old version is there. It has called the new version with the different set of local variables, including the argument itself. The argument itself is also different, as its own copy in the latest invocation. What does that do? It checks for the base case, still not solved, calls it again with a new set of local variables and a very different argument. At some point, what will happen? The problem will get solved trivially. For factorial, what would it be? It would be like 5 factorial is 5 into 4 factorial, right? So do you see how we divided this problem in a recursive manner? Define 5 factorial in terms of 4 factorial, right? 5 into 4 factorial. What is 4 factorial? 4 into 3 factorial. 3 factorial is 3 into 2 factorial. 2 is 2 into 1 factorial. But 1 factorial is 1. We all know that. So that could be the base case. And you say, okay, if you reach here, then just return 1. That's all. If we call the factorial function with 1 as input, you return 1. Don't call factorial again. That is where we stop the recursion. Who is waiting for us? 2 factorial is waiting for us, right? Because 2 factorial is 2 into 1 factorial. But 1 factorial comes back as 1. So now you can compute 2 factorial. There are no unknowns anymore. 2 into 1, 2. Return it to who? Factorial 3. because it is waiting on 3 into 2 factorial. 2 factorial comes in as 2. 3 factorial becomes 6. Then you go back to, you remove 1 by 1 from the stack. Then you get to 4 factorial, 24. Then 5 is 120. Right? That is recursion. So we will go over recursion again, and we will solve a few problems like factorial, Fibonacci, and we will solve a few backtracking algorithms. I will show you one backtracking algorithm in today's class itself. Then we move over to, and we will spend about 8 hours doing this. And I'll be giving you homework. Please solve and practice. It's a very good opportunity for you. If you spend the summer doing this, you will all find jobs very, very easily. And you will always remember this summer. Because will you do just one job? No. You will be changing jobs all throughout your life. Till you've gone into higher management, they'll only be asking you these questions. For your junior level dev position, intermediate, senior, principal level engineer, these questions will always be asked. So you will always remember this summer. That glad that I learned quite a bit that summer, and it's helping me even 20 years down the line. So please take this seriously and enjoy your summers, but also, enjoy with this. Derive pleasure from this. Sorting and searching algorithms. What is sorting and what is searching? When someone tell me what is sorting?
So arranging. What does?
Arranging.
Okay, and what is searching?
So looking for an element in an arrangement.
Correct. So they are both correct. So sorting is you sort something in an ascending or descending order, and the order depends on how do you define order. Right? You can define some kind of order for numbers or strings or whatever you want to sort. You can also sort structures. How can you sort structures? You have an array of structures, and to define something like go inside the structure, look at the last name, and sort descending on last name. You can set up that rule and you can sort that array. Right? You define the rule, you sort it according to that rule. What is searching? I mean, it's just a basic thing. You're searching for something. You're looking for somebody whose last name is whatever. And if you find, you're looking with a torchlight, and you figure this structure has somebody with last name whatever, and you say, okay, found. Right? It can take a lot of time. Right? You have to do it efficiently. So we were looking at some basic algorithms like bubble, insertion, selection. I think there are students here who already know bubble sort, because I saw some of you doing bubble sort in the class. Even for finding out of 3 numbers, which is the biggest, someone told me I'll do bubble sort. But it's just 3 numbers. Why do you want to do bubble sort? It will take longer than just doing if A is greater than B, B is greater than C, and that kind of a thing. Right? Just use the ternary operator, whatever, if else, and just do it. Instead, they were doing bubble sort. So then I saw that, okay, some of you already know bubble sort. Insertion and selection sort, I think I'm just going to do one of them today in the class to show you that these are not dangerous things. Almost all of you will be able to do this like trivially. And then we can go for advanced sorting algorithms like merge sort, quick sort, and heap sort. And these are also very easy. Contrary to what you might have heard from others or seniors, that these are all tough. Some teachers take 2 weeks to teach you merge sort. But believe me, I already did merge sort in the class. Some of you who used to sit at the front, maybe if you remember, we kind of did the merge part of the merge sort in class during our C lectures. And we did that in a matter of like 5 minutes. So merge sort will not take you more than half an hour to understand. Forget about taking 2 weeks to understand merge sort. It's easy. Okay. If you think it is easy, it is easy. If you think it is tough, then anything is tough. We'll do linear and binary search. Also very, very easy. Then we'll go for advanced data structures like trees. We'll majorly look at binary trees where each node can have 0, 1 or 2 children. Binary search trees, we will look at one of those in today's class. AVL trees and red-black trees. These are balanced trees. Trees can go out of balance and then they lose their property of log n searching. Trees are good because they help you search, like binary search trees. Search something really, really fast. But if the balance, they don't look like a tree, they just look like a list, like of one side going way deeper than the other side, then they're imbalanced. And to balance them, you can use AVL or red-black trees. We look at graphs. There are two ways of representing graphs. And then we will look at algorithms like BFS and DFS. I showed you one example of DFS. I will show you another one quickly today. Then we will look at some advanced algorithms on graphs like shortest path, Dijkstra's, Bellman-Ford, like from one point of a graph to another point of the graph, how to reach there with the shortest amount of cost. So the graph has nodes and edges, and the edges have costs. Right? What's the cost of an edge? It might be the length of the highway, it might be the condition of the road, it's like the cost of petrol and the petrol pumps on that road. It can be anything. From one point to the other, which route would you choose? Google Maps does that. And so there are two kinds of algorithms. We will learn both. We will learn about MSTs, minimum spanning tree. We'll be able to find a tree out of a graph, and don't get worried if none of this makes sense. It will make sense when we will do that. Prims and cross calls, there are more also what we'll be doing these two. And network flow and all of these different things. Then we will be doing dynamic programming. How many of you have heard of dynamic programming? How many of you get nightmares about dynamic programming? Because I used to get nightmares on dynamic programming because it's the most favorite topic of interviewers. Thinking in terms of dynamic programming is not trivial. It needs a lot of practice. To the tune that people usually remember solutions to these problems. They will just do 20 dynamic programming questions. They will remember each and every step and they'll go for interviews, hoping that one out of those 20 questions is asked. Have you heard such stories from other people? Anyone? Okay, that's good. Then you have not acquired that fear, and I'll not let you acquire that fear. Okay, whatever I said is just a lie. This is easy. Don't make this the biggest fear of your interviews. Don't do that. Because this is actually easy. But people will try to put false things in your mind that, okay, this is very tough. You'll not be able to do that. No, you'll be able to do that. Okay, we will look at the knapsack problem, LCS, coin change problem, and many other problems. We'll try to solve all of that. And then if we have little time, then we can go for tries and whatnot. But this is something that, we'll just do a quick review of.